Before the 18th century, metal components were comparatively small and were made by hand. Testing them was easy. They either worked or they didn't. Buildings were made of bricks, stone or wood, and transport was no faster than the horse. In the 18th century, Abraham Darby of Coalbrookdale found a way of smelting iron with coke, and as a result, objects could be made of cast iron on a large scale. For the first time, engineers could build structures out of iron. Machines and vehicles could be manufactured comparatively cheaply. The Industrial Revolution resulted, but metal structures became too large to test easily, and accidents occurred. As components became more complex and new materials were produced, structures failed and equipment became subject to fatigue and corrosion. The concept of fitness for purpose led to the development of minimum standards for the manufacture of critical components and joints. Destructive testing subjects components to extreme conditions to determine breaking point. Non-destructive testing is a crucial part of the quality chain. It ensures that components and joints are free of flaws which may adversely affect fitness for purpose at manufacture, and as part of routine maintenance for the lifetime of the product. Visual inspection reveals some surface flaws. Aids to visual inspection can reveal flaws in areas difficult to access, like this boroscope, which has a light delivered by a fibre optic, being used upon a rear spar from a Hurricane fighter, and tiny television cameras, here inspecting the tubes of a heat exchanger. But visual examination does not reveal some defects that impair performance and cause failure. Penetrant testing makes tiny surface flaws visible. A fluid penetrant enters surface breaking flaws by capillary action. After a dwell time of at least 10 minutes, the surface is cleaned off, removing excess penetrant. A white developer acts like blotting paper and draws penetrant out of a flaw. Red stain shows its position. Small components can be dipped in tanks and treated with powder developers. Fluorescent penetrants used with an ultraviolet lamp can show tiny defects, like these cracks in compressor blades. Magnetic particle inspection only works on ferromagnetic materials, most types of iron and steel that can sustain a strong magnetic field. In this example, an electromagnetic yoke generates a longitudinal magnetic field across a world. Defects that affect the flux lines attract magnetic particles sprayed on in an ink or dusted on using a powder. A white background helps identification. Prods can also be used where access is difficult, although here a current passes through the component and generates a circular field. Fluorescent ink under ultraviolet light, as used on this test bench, is more sensitive to smaller defects. Radiography reveals some internal flaws using X and gamma rays. X-rays are electrically generated in an evacuated tube. When a stream of electrons strike a tungsten or similar heavy metal anode, X-rays are emitted. They penetrate material and create a latent image on a film. In this Betatron equipment, particles are accelerated and when they collide with the target, very penetrating X-rays are produced. It is used to radiograph very thick steel components or concrete. An X-ray set is placed on one side of this pipe, and a film records the amount of radiation that passes through it, creating a double-wall, double-image shot of the world. Where flaws or anomalies interfere with the material thickness, more radiation gets through and shows up as a dark mark on the film when it is processed. Here, an X-ray is being taken on an aircraft engine nacelle, which has had a surface damage and needs further inspection. The technician sets up the shot and switches on from a remote control panel. Warnings are given during exposure. Pipelines can be inspected by X or gamma rays. The equipment is mounted in crawlers, which can vary in size for different applications, and can be articulated to negotiate bends. Crawlers are controlled from outside by weak radioactive isotopes. To start, they move down a pipe and stop at the required point, as in this demonstration. At a signal, the crawler emits X or gamma rays, and a film, wrapped around the pipe, records any flaws. Backscatter from low-energy X-rays is used in this modern apparatus to reveal water ingress and corrosion in the nose cone of an aircraft. A safe area around the aircraft must be roped off. Signals are presented remotely on a VDU to show layers of the component in much the same way as a CAT scan does in a hospital. The inspector watches for defects. The display is hard copied for analysis. Gamma rays from a radioactive isotope are often used instead of X-rays, as no power is required and they are portable. The isotope, in this case iridium-192, emits gamma rays continuously, so it is housed in a safe container. Guide tubes are fitted, and the isotope can be wound out to the end of the guide tube when required. A film is wrapped around the world on this pipe flange. The end of the guide tube is positioned inside the pipe. The gamma tip is wound out. And after a prescribed time is wound in. This creates a single wall, single image radiograph. When radiography is carried out on site, a prescribed area has to be marked out and cleared of personnel. Deep inside this oil industry processing module, a pipe weld is being checked. First, identification tags and IQIs, image quality indicators, are fitted to the film. Ident tags are lead letters and numbers. IQIs are graded wires, which show the sensitivity of a radiograph. The film is placed in position, and the end of the guide tube is positioned on the opposing side, giving a double-wall, single-image picture. Once the area has been cleared of everyone except for the radiographers, and an audible warning sounded, the iridium tip can be wound out to take the picture. Processed radiographs are interpreted with an illuminated viewer, and defects recorded, marked up, and if necessary repaired. Gamma rays penetrate both walls of this pipe at the top of the module. This will give an image of both sides of the world, double wall, double image, ellipse method. Ultrasonic testing can measure the wall thickness of a component when a pulse is transmitted. Bounced off a back wall and received by the same probe. A standard A-scan floor detector is used on this pipe bend to check for internal erosion. Digital thickness meters can record a series of readings in memory for future evaluation. Bolts in the wing of an aircraft are inspected with an ultrasonic set for possible cracking, although access is sometimes difficult. Through thickness application, one probe transmits and one receives to examine the elevons of Concorde for water ingress. A special jig is used to hold the probes. Low-frequency ultrasound is used to test bonding between the skin of an aircraft engine nacelle and the integral honeycombing by recording resonance, a process known as mechanical impedance analysis, or tap testing. Angled ultrasonic probes send a beam of sound into a weld from a distance to test for lack of fusion, cracking and other defects, which can be located using a special floor location slide. Complicated weld geometries can be inspected with ultrasound. Digital ultrasonic sets are increasingly being used in the field. Eddy currents are currents that are induced in conducting material by alternating magnetic fields from a coil in a small probe. They are closed loops of current which are perpendicular to the magnetic flux. If there is a defect or flaw, it will affect the coil, causing an indicator needle to flick. This aircraft wing is being routinely checked for fatigue flaws. Small defects can very quickly become major fatigue cracks. A CRT displays signals from a probe in this examination of a jet engine. The movement of the dot indicates whether a flaw is present to the skilled operator. A probe with a revolving head is calibrated on a special block with artificial cracks before checking the bolt holes of an aircraft wing. Cracks can spread from bolt holes to produce major failure. With the improvement of analytical equipment, the use of eddy current testing in heavy engineering is increasing. In air,
16,
and underwater. The diver moves a probe over the pipe. He has communication with the surface operator, who can also monitor him from a camera fitted to his helmet. The signals are computer processed and presented on a VDU for interpretation. Non-destructive testing is an indispensable part of any quality system in revealing flaws that might interfere with safety and fitness for purpose of machines and structures. But all NDT equipment needs to be checked regularly as part of quality assurance, and proper training is paramount to get the high standards required. TWI's School of Applied Non-Destructive Testing, based near Cambridge and with training facilities worldwide, offers a range of courses for all types of non-destructive testing techniques, leading to internationally recognised qualifications. Disasters still happen. Faults can have terrible consequences. As installations become more complex, more can go wrong. Quality control makes this less likely. In the 100 years that non-destructive testing has been practiced, it has saved large sums of money, extensive damage to the environment and many human lives, and is an essential part of quality assurance.